How are you, my friends? This is Basic Math Terms, part 26 about matrices. And these are coming from pre-calculus course lectures 31 to 36. You can always go and check the playlist Basic Math Terms for other parts. The terms here are matrix, dimension, entry, row, column, augmented matrix, coefficient matrix, Gaussian method, row-echelon form, main diagonal, Gauss-Jordan method, identity matrix, inconsistent, dependent, singular, non-singular, minor, cofactor, determinant, and triangular form. Now, when we say what is a matrix, simply it is a rectangular array of real numbers. We have real numbers in a rectangular form. It can be square like this or rectangle. We have some numbers there. They can represent anything. The dimension D is m by n. We don't say m times n. We say m by n. Like this is 2 by 2. That means the first number, 2 rows, row 1, row 2. Second 2, column 1, column 2. This one, B, matrix B is the dimension 3 by 1. Row 1, row 2, row 3, 1 column. And this is 5 by 3. So M here is the number of rows and N is the number of columns. Each number, each member, each element in the matrix, we call it entry. Now, we can add matrices and also subtract them, but they have to have the same dimension. Some books, they say same order or same size, but the best word is same dimension. So number of rows equals number of rows, number of columns equal number of columns. The sum or difference of two matrices of different dimensions is undefined. So we cannot add or subtract matrices with different dimensions. If we have a system like this, a linear system of equations, we can write augmented matrix and we can write coefficient matrix. In some methods, we have to use augmented, like Gauss method, Gauss-Jordan method. Another method in the inverse, we have to use coefficient. Look at the difference. Here we have 3 by 3, 3 equations, 3 variables, x, y, and z. If we write all the coefficients, 1 minus 1, 6, minus 1, 7, 0, 5 minus 3, 2. And then we write here a bar, line, or some books, they don't write the line. The numbers at the end here, the last column will be the constants, minus 11, 0, 31. So even if you have a line or you don't have a line, the last column here will be the constants. If you write it like this, we call it augmented. Coefficient, the same coefficients here, but we don't write minus 11, 0, 31. We don't write the constants. It's only 3 by 3. We call it coefficient matrix. That's the definition. Gaussian elimination method with back substitution. Gaussian is a German mathematician. He has invented this method. We write the augmented matrix to solve a linear system by matrices. Then we change it to row-echelon form. We use row operations to rewrite the augmented matrix. We write ones in the main diagonal and zeros under the main diagonal. I will show in the next slide here. This is what we call the aim for 2 by 2 in Gaussian elimination method. So we write here 1 in the main diagonals here, all ones in the main diagonal. This is the main diagonal here, and zeros under. If you have 3 by 3, you have 1, 1, 1, and then zeros under. If you have, and so on. So you can have 4 by 4, 5 by 5, 6 by 6, 7 by 7, etc. And these numbers, 1, 2, 3, these are the steps. This is step 1, this is step 2, this is step 3. I will show you now an example. And if you have 3 by 3, you go 1, 2, 3, and then you go to this one, 4, 5, and 6. Let's look at this example on Gauss method. Solve the linear system using Gaussian elimination method. 3x plus 4y is equal to 1, x minus 2y is equal to 7. First, we have to write the augmented matrix, which is the coefficients here, 3, 1, 4, minus 2, and then we have to write 1 and 7. See, this number here, 3, should be 1, because we know the aim here, I wrote for you, the aim for the Gauss, it should be 1, 0, 1, in order. So we can interchange the two rows that we have here. So we can write 1, minus 2, 7, 3, 4, 1. So this is 1 already. This one we have to make it 0. So I multiply row 1 by minus 3, which is the opposite, and then I will add. So minus 3 times 1, minus 3 plus 3, 0, minus 3 times minus 2, 6, plus 4, 10, minus 3 times 7 minus 21 plus 1 minus 20. Now this is 1, this is 0, this should be 1. So I divide by 10. So I get 1 and minus 2. Now look at the second row here. 0x plus 1y is equal minus 2. So y will be minus 2. So easy. Now we can use back substitution in row 1. So I can write x minus 2y is equal 7. Replace y there. I will get x equals 3. So the solution will be 3 and minus 2. X first and then y always. Gauss-Jordan elimination method, very similar to Gauss method, maybe 75% similarity, but only one difference I will show it to you now on the aim. See, in the Gauss, we have 1, 0, 1. We don't care about this number 0. It can be A and B and C. So we have to make it 0. That's the only difference in Gauss-Jordan elimination method. Also in 3 by 3. So we have to make ones in the main diagonal, and above the main diagonal and below the main diagonal, we should have all zeros. So we can start. You see these green colors here. This is Gauss method. 1, 2, 3, 4, 5, and 6. Then you continue 7, 8, and 9 to make them zeros. Then you will have x is equal to d, y is equal to e, and z is equal to f. Let's see extra example here. Solve the system x over 6, little more complicated, plus y plus 5 over 12 is equal half. 2x over 7 minus y over 14 is equal minus half. Solve the system here using Gauss-Jordan elimination method. For sure, you have to know what to do first. We have to rearrange it. So the LCD here, 6, 12, and 2 is 12. So you multiply by 12, the first equation on both sides. Second one, 7, 14, and 2, the LCD is 14. Multiply on both sides by 14, you will get this equation. Now you can write the augmented. 2, 4, 1 minus 1, 1 and minus 7. See, this one is 2. We have to make it 1. This 4 is not 1. So we cannot interchange two rows as we did in the Gauss example. So here we have to divide by 2. There is no choice. Divide by 2, divide by 2, divide by 2, you get 1 half and half. And then after that, you multiply by minus 4, because this is 4 here. The opposite will be minus 4. If you have here minus 4, you multiply by 4, row 1, and then you add to row 2. So you'll get 0, and then you can check these fractions easily. And then you have 0 minus 3 minus 9. Divide by minus 3. Or multiply by 1 over minus 3. So you get 0, 1, 3. See, we don't stop here. Gauss, we stop here. We continue to make this half 0. So this is 1 and this is half. The opposite of half is minus half. So I multiply the 1 here by minus half, and then I will add to row 1. So I will get 1, 0, 1, 0. So I can say directly x will be minus 1, y will be 3, and this is the solution x and y. This is Gauss-Jordan method. This is the summary of the special systems. Sometimes we have a single solution, or number two, we have no solution, then the system is called inconsistent. And if we have infinitely many solutions, we call the system dependent, if the rows are fewer than the number of variables. Like we have x, y, and z, 3 variables, but we have only 2 equations. In this case, we will have infinitely many solutions, and we call the system dependent. The steps here, if you want to remember the steps, rearrange the system if it is not arranged, write the augmented matrix, use Gauss or Gauss-Jordan aim, and then write the solution at the end. What is an identity matrix? All this here is the definition. Identity matrix, ones along the main diagonal and zeros elsewhere. So we can have identity matrix for 2 by 2. We call it I2, 1, 0, 0, 1. Only by itself, we call it identity matrix. For 3 by 3, we have I3, we have I4, I5, I6. Okay, every square matrix, we have an identity. The inverse now, if you need to find the inverse, the matrix should be square. Square matrix means n by n. Yeah, 2 by 2, 3 by 3, 4 by 4. You cannot find the inverse for 3 by 4 or 2 by 7. If the inverse exists, then you can multiply A times A inverse. The answer should be the identity. Remember, that's important rule. Also, A inverse times A will be the same as the identity. Now, in the inverse, A times A inverse, same as A inverse times A. Both should be equal to the identity matrix. Singular has no inverse. See, singular. Singular means like single by itself. If you have a matrix, sometimes there is no inverse. You have to check the lecture to see examples there. But singular means no inverse. Its determinant is 0. Non-singular has an inverse. Now, what is a determinant? Determinant is a real number. So it can be 5 or half or -6 or 0 or 1 or 100 or -50. It's a real number associated with each square matrix. Like, for example, the determinant of this matrix A, 9, 10, 4, -5, the determinant, we write 2 bars here. The determinant is -85. Okay, for 2 by 2, we have a formula. If A is A, B, C, D, then you can find the determinant. You can write DET of A. You can write 2 bars, but you read it as determinant. You multiply the main diagonal AD minus the other diagonal minus BC. So for 2 by 2 determinant is the product of the entries on the main diagonal minus the product of the entries on the other diagonal. Okay. Now, what is the difference between matrix and determinant? Big difference. This is important remark. Matrix is an array of numbers. So we have here square brackets, A, B, C, D. You have to write square brackets to show this is a matrix. But if you write vertical bars here, 2 bars like this, that is a number. Even if you have A, B, C, D, so the determinant is a single number. Determinants, they have vertical bars. Matrices, they have square brackets. Do not be confused, and you have to write it correctly. Minors and cofactors. If A is a square matrix, then we have entries inside, right? If we look at the entry Aij, then we need the minor sometimes. Capital M, Ij is the determinant of the matrix obtained by deleting the ith row and the jth column of A. Cofactor has a formula I will explain now. Capital C cofactor Ij will be -1 to the power I plus j times capital M Ij. Let's look at this example to understand more minor, and cofactor. If we have matrix capital T, 3 by 3, 4, 7, 6, 3, 0, 10, 2 minus 2, 5. Minus 2, you see this number here, minus 2, is located in the third row and second column, correct? If I need the minor of minus 2, see in matrix T, we have 9 entries or 9 elements, okay? Each entry, each number has a minor and cofactor. So the minor of minus 2, we have to delete the row and the column at minus 2. Then we are left with 4, 3, 6, 10. Then we find the determinant only. 4 times 10, 40, minus 6 times 3, 18. So the answer is 22. So 22 is the minor of minus 2. Now, if you need the cofactor, you have to find the minor first, because cofactor C32. From where we get 32? Third row, second column. It will be according to the formula, minus 1 to the power I plus j, 3 plus 2, 5. Minus 1 to the power 5 is minus times the minor, M32. We have found already 22, so it will be minus 22. We can use minors and cofactors to find determinants of 3 by 3 or more. Now, there are 9 determinant theorems that they were mentioned in lecture number 36 of the pre-calculus course. Remember, the matrices should be square matrices n by n. You can check the first 7 in the lecture. I put here only 8 and 9 to explain determinant of the inverse. Determinant of the inverse, it will be 1 over the determinant of A. So it is the reciprocal of the determinant of A. This is theorem number 8. Number 9, I have to explain the word triangular form, upper or lower. If we have any matrix A, square matrix, 3 by 3, 4 by 4, 5 by 5, etc., if it is written in triangular form, see, like this is a triangle here, upper or lower, below the main diagonal zeros or above the main diagonal zeros, then it's enough to multiply the elements or entries or members or numbers on the main diagonal to find the determinant. So 5 times minus 2 times 7, this is minus 70, is the determinant, if you have it only in triangular form. So it is the product of entries on main diagonal. Thank you for watching. If you like the video, you can subscribe and share it with your friends. I hope I can see you in another video with another topic. Thank you guys for listening.